So yes, I'm Gaetano Panagia. I'm a technical marketing engineer with Hamamatsu Photonics Europe. And today I want to show you a few techniques that are applied, spectroscopical techniques that are applied to precision agriculture and food analysis. Just a few words about Hamamatsu Photonics. For those of you who are not familiar with the company, we are a Japanese company, and we produce optoelectronic components. So we produce light sources and semiconductor detectors, but also complete systems. What I would like you to focus on this slide is that we have more than 15,000 products in the market, and most importantly, that 2/3 of these products are custom specific. So we always welcome customization requests from our customers. But diving in the topic of today, I've identified a few challenges that may affect this market. One of these in farming, for example, is the optimization of production yield due to a growing population. Of course, we need to adapt to climate change with more and more harsh events and difficult climates to grow our food into. And then, of course, we have the final goal of minimizing pollution with any activity that we start. And I think the spectrometers can help definitely to tackle all these challenges. We've already described a little bit how diffractive spectrometers work. So basically, the light reflected from a sample is split, is dispersed into its wavelength components, and then each component is focused on a specific pixel of a linear image sensor. So that's how we get the information about all colors, all wavelengths of a sample. And this wavelength contain very interesting information, specifically when we analyze a crop, as we've seen with the previous speakers, there is parameters like the green chlorophyll index or the red chlorophyll index, which are measured at 530 and 730 nanometers, that can be used to assess and map crop health. And this can be done using UAVs, so using drones, as we saw. Can also be done using tractors that can use the information to optimize fertilization, for example. And this can happen even more easily if the device that measures these wavelengths is as small as your fingertip, like the one that you're seeing in this slide. But this is not the only application that these small spectrometers can have in agriculture. In fact, another possibility of use of this is in water quality analysis. Of course, we use extensively water to irrigate our crops, and also we need to collect water back and analyze it if we applied, for example, chemicals in the field and we want to check for water quality after the farm. And this can be done again with these extremely small devices, pairing them up with xenon flash lamps, for example, in this lab setup that we have developed, in which you can see this is fiber coupled, and you have several vials with different chemicals. Specifically, we have nitrite, nitrate, and BOD. And this is measured using the light coming from a xenon flash lamp, which bounces back at the end of this holder. It crosses all the samples, and it's able to measure the concentration of each of them. This is a practice that would be done normally in a lab, so it will require some time to get the results. But with such a small device, these results can be obtained instantly. Other challenges in the food processing industry may be to establish nutritional values of our food, to detect possible adulteration. So, for example, if we have high-value goods like olive oil or wine, and this can be tampered with lower quality chemicals in it. Or we need more and more today to track the origin of food. So we need kind of a fingerprint that tells us what's in any kind of substance that then is used in the food transformation chain. And for this, we also have a solution, and this is a spectroscopical solution again. It's not a diffractive-based spectrometer, but this is a Fourier transform near-infrared spectrometer. You can see in this little video that I have that we are measuring in real time, we're distinguishing in real time the composition of this powder, which can be sugar or can be aspartame. And this can be done at 175 frame per second. So it can be done in line, basically. So it's very useful to analyze the ingredients in food. The principle through which this work, we have again light which is reflected off a sample. This light gets into this little scheme here. We have a beam splitter. So the single beam coming from the sample is separated into different arms, so into different beams. One reflects off a fixed mirror, while the other one hits a movable mirror, which is our special MEMS technology. And when these two arms recombine, they create an interferogram. So this kind of figure. So signal intensity and relative mirror position. It's what you can see in this graph. When we run a fast Fourier transform over this interferogram, that's when we get the absorbance spectrum of the sample between 1,000 and 2,500 nanometers. So this is what you're seeing here to the right, the one that gives us the possibility to distinguish between sugar and natural sweetener, so aspartame. This device can be, this kind of technique can be used in other applications. For example, you can imagine if you are a dairy producer and you're getting milk from several farmers, so from several sources, you want to check each raw material for homogeneity, for example. So you want to check your raw material before you put it into your product, before it enters your production. Another case could be determine the price of animal feed, which is an important application because the price of animal feed is determined by its nutrients. So how much proteins, how much fat, how much moisture is in animal feed. So using such a device or using Fourier transform spectroscopy, we are able to establish how much of these components is in animal feed, and then we can determine the price for it. The last challenge that we see in this market is bridging the gap between the end user, which has the knowledge about the application, and the technology providers, like we are, many in this room today. So at Hamamatsu, we think we can offer the bridging of this gap because we are producers of light emission components, we are producers of light detection components. We have the know-how to integrate this together into an optoelectronic module, and we can also make this module customized for the need of the application. So we have this new service that is called Pilot Line, in which we want to do exactly that. So combining our different components to make a prototype and make this prototype with a specific design intended for final mass production. So definitely what we want to do for you is to bridge the gap between your knowledge, your application knowledge, and our photonics know-how. Thank you so much.